is now being recorded.
As Jennifer noted, works for the U.S. EPA Office of Research and Development, particularly their National Center for Environmental Assessment. His offices are in Arlington, Virginia, or as you'll know, the particular area, Crystal City, just overlooking the Washington National Airport. The EPA focuses on assessing and managing the potential impacts of climate and land use change on water, water quality, and aquatic ecosystems. Prior to being at the EPA, Tom worked at the Academy of Natural Sciences in Philadelphia and was an American Association for Advancement of Science Technology Policy Fellow in Washington, D.C. He has a PhD from Penn State University and a master's from Colorado State University, and he has a BA from the University of Colorado. And with that, Tom Johnson.
Great. Thank you, Tom, very much for the introduction. And thanks, Roy and Kwasi, for the opportunity to present as part of the Cyber Seminar series. And finally, thanks to everybody on the line for calling in. It's great to be here. So what I've prepared for today, I think I have about 25 slides, is a brief overview of a project that I've been working on as part of a larger project team for about, the better part of the last 3 or 4 years now, that we refer to as the 20 Watershed project. I guess I'd like to begin first by acknowledging my co-author, John Butcher at Tetra Tech, as well as the many others that have contributed to this work. It's been very much a team effort and a pleasure to work with this very talented group of people. So that said, what is 20 Watersheds? Basically, we went into this project with 3 general goals in mind. First was to assess the general sensitivity of U.S. streamflow and water quality, specifically nitrogen, phosphorus, and sediment loads, to climate change across a range of plausible mid-21st century climate futures. We also wanted to consider climate change in the context of other watershed stressors. So we wanted to look at the potential interactions of climate change with increasing urban and residential development in these watersheds particularly. And then last, to try to understand or get a better feel for the implications of some of the different methodological choices involved in conducting these kinds of climate change impact studies, specifically things like the different watershed models, different climate change scenario data sets, these kinds of things, just to try to better understand how we might improve the way that we use models to understand climate change impacts. So these are the 20 sites. Let's see. They were selected. There were a number of criteria that we used to pick these sites. They were intended to represent sort of both geographic, hydroclimatic, and physical characteristics across the country. We ended up also picking sites based on practical reasons as well. However, just simply where there were data sets. Of course, you need adequate hydrologic stream gauge data to be calibrating these models. Particularly, the water quality data was limiting. So we had to be in places where there was water quality data, having an appropriate, an adequate number of meteorological data sets, and also where there were existing models. As I get into this, you'll see this was a big effort, and we did everything we could to try to work in places where there were existing water models that would just make it a little bit more efficient for us. We could use those as a starting point and do whatever additional work we needed to get those set up and be consistent across the whole set of sites, but also not starting from scratch. So just kind of in a nutshell then, what we did, we set these models up. We were running continuous daily simulations for streamflow, nitrogen, phosphorus, and sediment for 2 time periods, approximately 30-year time periods. Our historical or baseline period was roughly 1971 to 2000. It varied a little bit with the sites depending on what was available. And then the future that we were looking at was this 2041 to 2070 period, which is representative of mid-21st century. These were fairly large watersheds. They're roughly about a Huck 4 digit in size, in the order of about 15 to 25,000 square miles. The models were set up at about a Huck 10 scale, and then we're reporting data back only at about a Huck 8 scale. So fairly large. This is larger than a lot of these studies that are done at a much smaller scale, and accordingly include a little more detail on some of the site-specific kind of factors in those watersheds. This was intended as a little bit broader kind of look at regional hydroclimatic change across the country. So what we did in each of the 20 sites that I just showed on the map, we ran watershed simulations using SWOT, the SWOT model, version 2005, looking at the individual and combined effects of climate change in urban and residential development scenarios. I'll say a little bit more about this later, but basically the climate change scenarios that we looked at or the climate scenarios we looked at were a baseline scenario, which was basically this 1970 to 2000 period, and then 6 dynamically downscaled futures that we acquired from the NARCAP, from the National North American Regional Climate Change Assessment Program, which is run out of NCAR. We acquired some of the data that they've been developing over the last few years, and I'll say a little bit more about that in a minute. The land use, we had one future urban and residential development scenario that looked at that we acquired from a project that's been going on here in my office. This ICLUS project, which is an acronym that stands for Integrated Climate and Land Use Scenarios Project. So in all 20 watersheds, we ran SWOT looking at, again, the individual and combined effects of these different climate, 6 different climate and 1 land use scenario. We then went on, and in a subset of the 20, in these 5 sites, which we refer to as pilot sites, we ran some additional climate scenarios. There are 8 additional climate scenarios that were run. 4 were based on non-downscaled GCM output. 4 were based on statistically downscaled GCM output, but based on the same parent GCM. I have a slide later. It's a little bit confusing, but I have a slide later that shows how this is all laid out. But these were some additional climate scenarios that were just exploring the variability that you might see associated with use of different climate scenario data sets. We also ran independent simulations using a second watershed model, HSPF, another common, widely used model that we thought would be interesting. It's common practice to be looking at ensembles of different climate models, and there's a lot of variability associated with scenarios that come out of these different climate models. We wanted to just look at what the implications, how different results would be if we were to use a second watershed model, which has been done in a couple of cases I'm aware of, but this is the first I've seen it in looking at climate scenarios. So yeah, and then in these sites, what we used these additional scenarios for was just to try to get a better understanding of some of these methodological issues related to conducting climate change assessments and what the implications of that were. So just very quickly then to say a little bit more about the climate change scenario. So focus on the figure here on the left. What it is, each one of the cells in this box represents a scenario, and what it is that we had there were 4 different what I'll call parent GCM models. These are the models that are used in the NARCAP data set, and we developed our scenarios. We had these 6 NARCAP scenarios in the pilot sites. Then we also had the 4 scenarios based on the same parent GCM, but not downscaled. So we were basing our scenarios off of the raw GCM output. And then we also had scenarios based, again, on the same parent GCM, but statistically downscaled that we acquired from this BCSD data set that many of you are probably familiar with. It was put out by Reclamation, Santa Clara University, and Lawrence Livermore a number of years back, and has been widely used. So this is our basic structure, and this allowed us to do some comparisons where we could look at a single GCM in the results that we are getting from a single GCM run in some cases here, and just scenarios that were generated based on different approaches for downscaling. To implement the scenarios in the water models, we used a change factor approach. which is essentially a kind of a simple statistical downscaling. Basically, we interpolated the climate model output to NCDC weather stations that were used in the watershed models. Then we then calculated mid-21st century changes relative to baseline that could be associated with each one of those weather stations. And then going back and looking at historical data, we used the historical data at each one of those stations and just adjusted that to reflect the changes that were projected by these different climate models. So that's a fairly common and a fairly simple way to be developing climate scenarios, but I think there are some advantages to that, which I kind of like. It's kind of a hybrid approach. The scenarios that we adjusted specifically were temperature, daily air temperature, precipitation. We adjusted both the volume of precipitation, where to reflect what was projected by the climate models, as well as the distribution of precipitation within different events. This is something that you see common in the climate model output, is that in addition to changes in precipitation volumes, that it's projected that there'll be a greater proportion of precipitation occurring in larger magnitude events. So we actually, from the NARCAP data, were able to calculate the changes within different event size classes, and then we used just kind of a mass balance approach to adjust these historical data, so we achieved not only the total mass balance, but we achieved the mass balance, projected future mass balance within different event size classes. And then we also included solar radiation, humidity, and wind speed in our climate scenarios, because we were using the Penman-Monteith approach to calculate ET, and those are variables that are required in that calculation. So we wanted to use a fairly rigorous approach to doing ET, because thinking that's likely, results are likely to be sensitive to that. So we wanted to try to do a good job with that. And then lastly, in the SWOT runs, we were also representing changes in atmospheric CO2, which is, I'll say a little bit more about this later. There's some kind of interesting results there. But there is an existing capability in SWOT to adjust the CO2 concentration, which affects both plant growth as well as the water loss, evapotranspiration related to the leak of stomatal conductance and the way that the physiology of plants that affects water loss. So we did also represent this increase in atmospheric CO2, which is consistent with the climate scenarios that we were looking at. Briefly then, the land use scenarios. We had this one land use scenario that was developed based on a projection from EPA's ICLUS study. I mentioned ICLUS is just an acronym. It stands for Integrated Climate and Land Use Scenarios. And briefly what this is, it's a project that was developed to look at, or to develop projected changes in urban and residential lands in a way that's consistent with the underlying assumptions behind the IPCC emissions scenarios, which are used to drive climate models. So basically what that allows you to do is develop a coupled climate and land use, coupled and climate land use change futures that are based on a common set of assumptions. And there's a report out there where that website that's listed, and there's quite a lot that's available on this if anybody's interested in looking up where this data set is and what it's based on. But this is where we drew our land use change scenario from. And we to be consistent with the climate period that we were looking at, we just used the 2050 projection from ICLUS, and for the A2 emissions scenario, which actually, I'm sorry, I should have mentioned that earlier. But with our climate scenarios, we were using the NARCAP data, which only is available for the single greenhouse gas emissions scenario, what's referred to as the A2 greenhouse gas emissions scenario, which is based on, it's a relatively pessimistic set of assumptions, resulting in relatively high emissions of greenhouse gases. So the climate portion is a little bit higher with that one. So that's the underlying assumption about greenhouse gas emissions that are inherent in this book. So then just a couple of other just quick things about the modeling. We also, all of these sites had dams and reservoirs in them. We were not able to represent everything in great detail, but we did go in and we did try to represent major dams and reservoirs, things that we estimated might modify flow greater than about 1%. Point source discharges were also included, again, just the larger point source discharges that we pulled out from the PCS database that were greater than about 1 million gallons per day. And then some things that are not represented. We didn't do agriculture. That's something that was just beyond the scope of this, and I could say a little bit about that in the end, just kind of how I interpret these scenarios as being useful. And then we also didn't represent water infrastructure management in great detail. We did represent withdrawals and diversions to some extent, but if you were to go into any of these places and look at a finer scale, we did make some simplifying assumptions here, just because these were intended really more to look at kind of broad hydrologic change, kind of broadly across different regions of the country. So we weren't trying to set these models up in great detail with all of the processes representative. So I have just some slides I want to flip through and just kind of give a snapshot of the results. There is a report that I have a website at the end that includes all this information. So I don't want to spend too long on this, but I guess I'll just kind of flip through some of these slides and illustrate some of these things that we're seeing. And if anybody has questions at the end, I'm happy to answer that. But like I say, there's some other sources I'll give at the end that people can go and kind of flip through this information in their own places that you care about or that you're interested in as well, if you'd like. So just kind of as a quick snapshot, this is a figure showing projected temperature changes. These are from the 6 NRCAP scenarios, this mid-21st century time period. And the way this is set up is that the 20 different sites are organized. They're just sorted on the x-axis there based on the median value from lower to higher median value. So what this shows is just basically that, across these 20 sites, the projected changes for mid-21st century were on the order of about 1.5 to 3, maybe a little over 3 degrees Celsius with some degree of variability. But relatively speaking, they were pretty consistent. All of the models agreed that there would be warming. This is the same figure for precipitation. Again, the 6 NRCAP scenarios. The sites, again, are sorted according to the median value from lowest to highest. So the order of sites in each one of these plots I'm going to show along the x-axis is going to be a little different. It's just a little, I think, easier to look at when you sort them this way. And then just one other thing to note is that the unit here is expressed as percent of baseline. So 100% there means basically that's equal to the baseline condition, this 1970 to 2000 period. And then, for example, 120 would be about a 20% increase, and 80 would be about a 20% decrease. So that's just the way the units are, and that will be consistent in several of the next slides. So in this case, the range is a much greater range in the order of about -15 to plus 20%. You see that there's a much greater variability even among these 6 scenarios, which isn't a huge ensemble as these kind of climate studies go. You see quite a range there. In many cases, within a given site, some of the models are showing increases, some are showing decreases. So that's something that will carry over to the hydrologic simulations, and we can discuss later. So moving on, then, this is just looking at some of the watershed, the simulation results. Here we're looking at the total stream flow in response to the 6 climate change scenarios. So just holding land use constant for the moment here. Again, we have the sites organized just along the x-axis, just sorted, from based on the median values from low to high. This generally it correlates fairly well with the changes in precipitation. Largely seems to be driving this. You do see, as is I think common in many of these kinds of studies, there's a multiplier effect that precipitation change in the order of 5 or 10%. It's often you see a greater response hydrologically. With mean flow, we're kind of reflecting just the basic moisture kind of water budgets for these mallets. As we get into some of the other endpoints, it'll be interesting to see that there's some more subtle things going on when you look at the high flows and low flows that I think are related to changes in the seasonality and changes in the particular watersheds, how they store and release water, which is kind of interesting. But I just wanted to put this up just as kind of a snapshot, just showing, again, thinking of this as like a regional picture, on the order of about plus or minus 50% in water yields we're looking at. There's a cluster of them, if you look at these median values down here, that appear to be getting drier, largely in the southwest. There are some that appear to be getting wetter, and then there's a number of them that are kind of in the middle there. Just kind of a snapshot of nationally what some of these projected changes are. Again, here, this being based on the SWOT simulations using this consistent methodology and set of scenarios. So here's a similar plot. This is looking at the 7-day average low flow response. The figure works the same way. The units are based on percent of baseline, so that 100% there is equal to the baseline condition. Increases are above that point, and decreases are below. There's this outlier over here. Cook Inlet is a little bit of an outlier. You'll see that in all of these slides. I think basically it was getting a lot wetter in Cook, and I think that's largely due to the snow and ice there. That's being released with the warming, although there also were fairly significant increases, projected increases in precipitation for that site. So that's kind of generally what's going on here. But again, it's kind of a mixed signal. If you look at that compared to the baseline condition, or this 100%, that there appears to be a set of sites that, well, even within a given site, there are often scenarios that are plus or minus current conditions. There are set that seem to be looking like they might get drier, wetter. So same plot. This is the 100-year flood, so this would be the 100-year daily max stream flow. We did this. This was a kind of a traditional. We fit a log Pearson distribution to the daily data, and that's what this number reflects. And then again, the units are not the real numbers. They're just expressed as a percent change. Some funny outliers that I can't explain at this point up here with the it's actually the Neuse River. It's in this we lumped as one of our sites that the Neuse and the Tar were lumped as a single site, but the data that's being shown here is actually just for the Tar River. I don't know why that is so big with that model, and I'm forgetting right now. I have to go back and look that up which specific model that is, but basically, you're seeing again some fairly significant changes here. If you focus down here, on the order of plus or minus, at least sort of plus or minus 50%. In some cases, even some increases, sort of closer to 150% or a 50% increase. So then looking at the water quality variables, again, this is the format of this plot is the same. Again, the orders on the bottom are a little bit different, just sorted based on the median values. Again, an outlier here. In this case, it's for this Powder Tongue study area. This is actually data for the Tongue River. Again, some of these things we need to go back. I know I need to go back and kind of look into some of these outliers and try to understand specifically what's going on there. But again, it's kind of a mixed. You see again, as we have in all of these endpoints, that there's kind of a range across the nation. That it seems to be a set of sites. Generally, in this case, loads going down a little bit, and maybe a little bit more, sort of a broader trend towards increases in nitrogen. These do correlate reasonably well with the flow, the water yields, as you might expect. There have been some other studies that have showed that kind of thing. But again, just putting some boundaries on there. Again, changes on the order of about plus or minus 50%. Maybe a little bit skewed a little bit towards the high side, taking, stepping back and kind of thinking nationally what the distribution of these changes might be. Here's the phosphorus load, kind of the same story, and I'll just get through these quickly. And then last, the suspended solids load. In this case, the variability was quite a bit greater. But again, so I think these are just kind of providing a national, kind of a broad, kind of a, think of it as kind of a screening level understanding of what some of these potential changes might be. And while there are some questions that come up looking at this information, I think it's interesting. I mean, it suggests that there are, that in many of these places there are things going forward could be quite different than we've experienced in the past, and in some cases you could probably infer some changes in the change in direction and maybe magnitude in a general way, but there's still also a lot that needs to be resolved here, and there's a lot of texture in these results that I think reflect the different watershed and hydrologic processes that govern these different endpoints. If you look at, for example, a sediment response as opposed to a flood response or a low flow response, you can kind of imagine the different processes that govern those, what you're seeing there, and then think about the particular drivers, changes in the different climate attributes that are driving that, and go back and kind of piece it together. So that's just kind of a snapshot of the climate results. I wanted to just go through quickly some of these other goals that I mentioned in the first slide. This one is showing, again, the SWOT simulated response for our urban development scenarios. And there's not a lot of numbers on this slide, but I wanted to make just a fairly simple point, which is that at the scale that this study was done, the projected changes in urban development were quite small, and subsequently the projected changes in the streamflow and water quality endpoints were also small. That wasn't really a great surprise. So if you look, this is these red columns. We have the sites listed down, the first column there, and then if you look in these red numbers, the urban response. This was just a range. And this is expressed at the Huck 8 watershed scale. So within each one of these 20 larger study areas, there were on the order of about 8 or 10 Huck 8 sub-watersheds. And what this is showing is the range of projected changes, in this case for mean stream flow, among these Huck 8 scale sub-watersheds within each study area. And in most cases, they're very, very small. There are a couple where there were some larger changes here in Illinois. Trinity was an outlier. This was just one sub-watershed in the Trinity basin where there was a fairly large amount of development that caused, that drove that response. Interestingly, there's a couple of these that showed up as the negative, that with increasing urban development, that there was actually a decrease in stream flow. And basically, I think what that is we went in and looked at this, and that the reason that is the way it is because the model with the urban development, the land use that was represented there, the vegetation actually resulted in greater water loss than the native vegetation. So if you look at those, they're in the dry sites like Southern California, South Platte, Willamette. I don't know why that was in Willamette, but basically we looked at that, and I think that response is largely because the vegetation that was represented, things like lawns and urban open space, were resulted in the model, as the model represented, greater evaporative loss than the native vegetation. So that's why those numbers went down. So I think, kind of in a nutshell, that the urban, we're still working on this, but at the scale, at this initial scale that we're looking at, there just isn't, I think, a lot to say about the urban response. Clearly, at smaller scales, it's well understood that urban development has a very great impact on streams, and I know that goes on here, but we're still trying to parse this data, and we have some different ways that we want to try to look at this to say something more. I think it is interesting, this scale effect, that there, at smaller scales where development is more concentrated, is where these local, the effects of local disturbance, things like urban development, as well as point sources and other kinds of impacts, are going to be very prevalent. But then as you sort of scale up and you start thinking about these larger issues, maybe, kind of large basin water supply, maybe things like nutrients in the Gulf and dead zones and out at the mouth of large river basins, that's where climate change, might start to really become the dominant driver in terms of a management response, thinking about, because climate change is operating over these large scales. But this is all stuff we have a paper actually that we're working on that I'm hoping that we can sort of dig into this and say a little bit more about that going forward. So just shifting gears a little bit, I mentioned we ran in these what we were calling pilot sites. It's a subset of 5 of the 20 we compared. We did these independent simulations using SWOT and HSPF. This is just a comparison for total stream flow. This is looking at the entire set of scenarios that we ran. So there were 14 climate scenarios and the 2 land use scenarios, current land use and future, and they're all just kind of lumped in there. What we have are the, get my arrow there, the HSPF simulations are shown on the x-axis here and the SWOT simulations on the y. Again, it's this convention that where results are plotted as percent of baseline. So 100, this middle point right here is current, no change from current. And in this case, the models actually agreed pretty well. There is this general tendency of SWOT to be a little wetter than HSPF, and that is due to the representation of CO2, and I'll talk a little bit more about that later. But I think that's basically reflecting that in SWOT we did this representation for increased CO2. In HSPF, there isn't a capability for doing that. So we did not represent that in HSPF. But otherwise, the models agreed fairly well. We basically, as a more general statement, I think, both of these models, I think these were both calibrated and validated models. They both did reasonably well in that respect. I think the team felt that both of these models were doing a good, quote, good, acceptable job with these simulations. But there are some differences in how they're implemented, which you see, for example, that issue with the CO2. So here's just a similar plot for nitrogen loads, and there's more variability here, as you might expect. I mean, I think as you start trying to do water quality, there are many more factors that become important. Just the subtlety in the watershed, different watersheds. As well as the way these models are representing processes becomes more apparent. So I just wanted to illustrate in this case the models did not agree very well. You generally see these loads that SWOT was over predicting a little bit than relative to HSPF, probably because again the water yields were going up as well. So the nitrogen loads were correlated with the water yields reasonably well, but it is increasingly variable as you start getting into these water quality endpoints. Which, just a note, I think that shouldn't be a surprise to people that do watershed modeling. But some interesting, it leads to some interesting questions about as we're doing these assessments and kind of the variability associated with using different water models, watershed models, compared to the variability that you see across these climate model ensembles, and kind of what can we do going forward? Where what should we be focusing on, and how can we improve our understanding of what's really important in terms of making better management decisions. So just very quickly then, I mentioned the CO2 effect. This figure is just showing again it's for the these 5 pilot sites. What we did is we ran SWOT without adjusting the CO2, just assuming the current CO2, which in this case was 369 parts per million. And then we ran it also with this projected future CO2, which we used this 533 value, just to see what the effect of that was. And what's shown in these bars is the difference in the projected values for mid-21st century with CO2 as compared to without. So you see, there's a A lot of variability among the sites, but these differences are not insignificant. If you look at just in the ACF here, come the order of a 5 or 10% change in these across these different endpoints, where you have total stream flow, suspended solids, total phosphorus, and total nitrogen loads. Minnesota River, they were very, very large. Willamette River, not so large, but just something that's kind of interesting. A lot of, in the agricultural community, a lot of agricultural models, they've been doing this for years, representing CO2. We know from the FACE work, a lot of experimental work, that there can be, changes associated with the atmospheric enrichment of CO2. My understanding, there's still some debate about the ecosystem level impacts. There's also a lot of uncertainty, I think, related to whether these effects will be expressed. You get into things like nutrient limiting. As it gets wetter, how will these effects of the increased atmospheric CO2 be expressed when you're also thinking about like nitrogen limitation and other factors that might influence the plant response. I sort of consider this as something that's kind of not understood very well, and would like to try to get a better sense. But at least if you look at the way that it's done in SWOT and represented in SWOT, which is, I think, goes back to these methods which were developed for the EPIC model. There's an equation by Easterling et al. That we used, and that it suggests that these effects of adjusting CO2, adjusting for CO2, could be quite significant in some places. So just something to note. And then this other point about downscaling. So here, again, this is a comparison. So we just wanted to look at the effect of using different climate scenarios based on different approaches for downscaling GCM output. I'll assume for the moment that most people are familiar what downscaling is and these different approaches. It's just basically a way to take coarser scale global climate model output and develop finer resolution data sets that can capture processes and variability that occur within that are within a single GCM grid scale. And there are statistical ways for doing that, working largely working with existing observational data, and then there are these dynamical approaches where you're nesting a regional climate model or a finer resolution climate model into a grid cell within the GCM, using the GCM as the boundary condition. Just basically running a more resolute model within the GCM. So what this is showing, we have, so again, there are these five different sites, these pilot sites. These are, if you look at just this one for ACF, the 4 different points there. And I'm sorry, we used a little different notation here. This is, again, these results are expressed as relative to the baseline condition. But here, instead of the previous slides, it was 100%. Here, it's 1. So this line here that's 1, this is equal to current. Anything going upwards from there is an increase. Anything going downwards from there is a decrease. And here we're looking at total, I think it's total mean annual flow. I'm sorry. But what this is showing is, so this is a single GCM run. Actually, it's exactly the same GCM run from the CGCM3 archive. And what we did is when we developed a scenario based just off of the raw GCM data, which is this green triangle, I'm sorry, it's the little X. We developed a scenario based off of the statistically downscaled version of this, and then we developed, we ran these scenarios based on 2 different dynamically downscaled scenarios, again, based off this exact same GCM run. You see the variability there. I think it's interesting that, one thing just to note in several of these sites is that among the dynamically downscaled results here, that in some cases you actually see that when you take the same GCM run, just using the raw GCM, it showed, in this case, decreases. The projected change in flow was a projected decrease. But when you dynamically downscale that with one RCM, you see something comparable to the GCM, but then with this other one, with the RCM3, you actually change the direction there. So it's adding variability, which again, it's not, that's no surprise really. You think, these models are adding, these are new models. They do things differently. They're adding this subgrid scale, representing these subgrid scale processes. So you would expect it to add variability there. But I think it just, in this, in our data set here isn't large enough to really address this in a rigorous way. But I think, it's interesting just to point out just kind of ballpark some of the ranges and variability that we're seeing associated. In this case, simply based, using the exact same GCM run, but just based on different downscaled scenarios, running it through our SWOT model and looking at the flow response. So, in this case, plus or minus 10%, I guess, in APF, and it kind of varies. In Minnesota, again, it was much larger range. This is the same exact data, just for a different GCM model, the GFDL GCM, but same idea, just showing the range of variability associated with a hydrologic projection based on climate scenarios from a single GCM, but downscaled using these different methods. I think, again, the message there, there is no, at least I'm not qualified or capable to say which of these is, quote, best. I think they're all sort of equally probable, equally good. But, by doing it this way, it's adding some variability to these results, and something that is, both interesting to consider in a decision-making context and also as I think a research context going forward. So just a few closing comments. I think as a first-order conclusion to this, I mean, the results, well, there's a lot of variability, and in a lot of cases, even within single sites, you see results, if you're thinking about like a water yield or a nutrient load, something that is important in the context of a water management goal. In a lot of cases, there's a range, and often the range is plus or minus to current conditions. Well, even given that uncertainty, I think what is pretty clear in these simulations that in many places that future conditions could be quite different from the past, and I consider that just kind of a first-order conclusion that it's better to at least be aware of an uncertainty than to think you know something and to go forward. And you'll get in a lot less trouble, or you are less likely to get in trouble if you are aware of what you don't know, and you can hedge and you can plan for that uncertainty as you go forward. So I think that's something that clearly comes out of this. And in many sites, but not all, there's I think a pretty well-defined envelope of responses, and in many cases you can identify a direction of change, which again I think can be very useful in the context of decision making. You can see there's variability nationally. This is, I think what we saw was fairly consistent with some of the larger scale studies based, for example, on the water balance numbers that come out of GCM, the climate runs, as well as some of the larger, these studies with a VIC model, for example, that are kind of running at a large basin scale and are very good at getting kind of a general, characterization of the kind of regional patterns of changes. But this is sort of using a different set of methods at more of an intermediate scale, and I think it's actually encouraging to see some of the similar trends. The drying in the Southwest, kind of a little bit wetter in the northern states, and then a lot of places where it's hard to really say much more hydrologically, and the water quality variables, which is something at EPA we're very interested in. I think that is just something that is even more challenging than doing the hydrology. But I think we're starting to develop, put some of these pieces together and develop an understanding of what these potential changes could be for endpoints like nitrogen and phosphorus and sediment. The urban development, I talked about wanting to do climate in the context of other existing stressors. Urban development is something that's very important to EPA. Thinking about what these impacts are, as well as trying to manage these impacts. At the scale of the study, it's a little tough. The result, as I showed, the projections just didn't suggest very large changes, and subsequently the the watershed response was not great. That's no surprise. But that said, I mean, I do think at finer scales where development is concentrated, there clearly will be impacts, and we're continuing to work on this. I think there is this interesting question about scale, different scales, and where well, it's a little bit of an ill-formed question, I think, to talk about, well, which is, what's more important, climate or land use change, because climate change effects only operate through whatever land use is on the ground. I think there is some interesting, there are some interesting ideas that might come out of this in terms of the, thinking about the different scales at which different types of disturbance are expressed, and that might be useful to watershed management. So, and then lastly, the thing about the methodological choices, our data sets were, we I think have a very nice data set here, but it isn't huge. But some of these questions about the different hydrologic models, the variability associated with the different downscaling methods, the effects of CO2, I think just raise very interesting points that, in addition, we tend in the climate community, we tend to think a lot about the climate variability, but there still are, I think, some very important questions related to how we do the hydrologic modeling, which leads into this last point, that this is still an area where there's a lot of work that I think is needed. Going forward, the models and the underlying science clearly can and will improve. I think those are important areas that we need to keep working on, but there will always be uncertainty too. I mean, this is something, at least in thinking about, what do we do with all this information? How can we use this to make better decisions going forward and to ensure that we, going forward, we're managing risk appropriately. I think, in addition to understanding, in addition to developing the science and models, I think we also would benefit from thinking about how we use models, warts and all, to better support decision making, and that means embracing uncertainty. One example, some other work that we've been doing here with this approach referred to as robust decision making that many may be familiar with. That we're working with RAND. Rob Lempert and the group at RAND Corporation has been doing a lot of work with this. It's just kind of an approach to quantitatively use these scenario-type simulations, coupled with a very broad assessment of management responses, to think about what we can do to be less, or to be more resilient to a broad range of future climates. We can put boundaries on these things, what we think might happen, but we aren't, I believe, I don't think we'll ever be able to put numbers on the future and plan on it in a real quantitative way. But, through approaches like robust decision making, thinking about how we can use models to better help decision making, I think is something that would be a very useful avenue for further work. A couple of other things, available information. There's a EPA report that we released just last September that's available. The website is listed there. Most of the data that I showed today is in there. There's some very detailed information about the model setup, calibration, validation, things, how we set those models up and so on. If anybody's interested in that, that's available. There's a couple. We're working on a set of papers. There's one that came out a little while ago in the Journal of Water Resources Planning and Management. That if this is just kind of a review of, it's actually similar to what I presented today, but written up in a little more detail. If anybody's interested in that, feel free to send me an email and I can send you a copy. But then we also have a few that are coming out. There's a paper that was just accepted in Journal of Hydrology that John Butcher, my colleague at Tetra Tech, has taken the lead on, where he's digging into this issue of representing CO2 in more detail, and he does some analysis showing what the implications of that are. And interestingly, he developed an approach in HSPF for adjusting some of the parameters in HSPF to actually do that representation of CO2. And then it does a comparison between a CO2 adjusted HSPF run and the CO2 SWOT run, and comes to some interesting conclusions there. So that should be published very soon. And then we have several others. There's a paper that we are getting close to submitting, looking in a little more detail at the land use comparison, also a little more detailed analysis on that downscaling analysis. So these things are pending. If anybody's interested, please do feel free to send me an email, or if you want to just call and chat or about any of this stuff. I'm always interested in people's comments, and would be happy to talk with anyone. And then just a last point, we've posted these simulation data sets also. It's on the iClues webpage. So the third item here listed this web address. What this is that the SWOT, we've posted the SWOT simulations for the 6 NARCAP scenarios at a Huck 8 scale within each one of these databases. So we're oh gosh, what is it? It's annual data for these different endpoints. So for each Huck 8, we have the 30 years of annual data under each scenario. So that's out there. If people are interested in kind of looking at that, if there's a particular place you're working or something you're interested in, feel free to go, download that, and that's something that we've made available. So that said, thanks very much. I think there's a little time left. I would be happy to answer questions, and otherwise feel free to contact me anytime offline if anybody is interested in this work.
Great, thank you, Tom. And Tom Meichner, do you want to kind of handle the Q&A? I see we have a couple of questions in the chat box there.
Sure. So, Tom, there's a question from Andrew Milway. 2 questions. The end scenarios show quite large increase in the Susquehanna, which will be of great interest to people concerned about the bay. Any comment on what drives that change?
Yeah, probably you're referring to nitrogen loads. I would think that's the big one in the bay. That one, I believe, there are the scenarios there. Well, you know what? I guess I can go back. A lot of these things are driven largely by the changes in precipitation. So my short answer would be that if you go here to
it's wetter.
Susquehanna, although we're kind of, the mean, so most of the precipitation scenarios we're showing increases here on the order of about 5, range from about current to about 10%. So that there's a strong correlation of nitrogen with the precip. Beyond that, I really can't say. We are doing there's some other work that we are doing actually with the Bay program with Lou Linker and Gary Schenk and the folks with the Bay model there, that running some scenarios to, particularly looking at some of the urban areas there and thinking about stormwater management. But I suspect this is, this response is probably driven to a large extent by the non-point loads. I guess I can't say much more about that other than that it's probably related to this, just the general increase in precipitation that's projected there.
And then his other question was the difference between downscaled and raw GCM models likely affect intense convective systems much more than mean flows because GCM resolution can't simulate that scale process that generates high intensities. Do you see this in your results when you look at the higher intensity storms?
Sorry, can you say that one more time?
Okay. So, right, the difference between downscaled, the dynamically downscaled, and raw GCM models likely affects intense convective storms more than mean flows, because the GCMs can't really simulate the processes that generate high intensities.
Gotcha. Yeah. Okay, I see what you're saying. Yeah, that's a really good point. That you would think that with those, at least the variability associated with those high. If you were to look at a high flow event, or for that matter a low flow event too, I guess, that the variability that you would see, I guess there would be 2 components to that. One would be just the individual characteristics of the watershed and how it stores and releases water, but then also the sort of subgrid scale processes that you're seeing that are represented in the downscale data that are not that are kind of averaged over with the GCM data. So I haven't, again, I'm not doing very well with these questions, but I don't know specifically, but I think, we do actually represent, because of this delta, this change factor approach, even the GCM, even the scenarios based on the raw GCM data do represent spatial variability because, I've forgotten, in the Susquehanna there were a lot of weather stations we had, I think probably 40 or 50 weather stations that were used in that model. And we were just superimposing these projected changes over each one of those weather stations. So we did get that, the spatial variability, but it's the temporal variability, and then sort of both the temporal variability and then also the kind of other spatial variability that you see in the downscale data that is not in that wouldn't be present in the GCM at the GCM scale that would drive that variability. So that's a great idea. I can't answer that question either, but you actually, it's a great point. I'll have to go back and look at those results in more detail with those specific, for those specific scenarios and see if there's anything that turns up there. Great questions.
Yeah. So from Eric Smeltzer, seems important to evaluate changes in assimilative capacity and not just changes in nutrient loading in order to water quality impacts from climate change.
Mm-hmm. Yeah, no, I agree. And here we're just looking at the loads, which are not, if depending on what you're concerned about, for example, if it's a concentration that you're more concerned about, if loads and concentrations go up in a proportional way, then concentrations are not going to change. So yeah, that's a good point. We just didn't, again, the goal of the study was just to try to capture some of the broad regional patterns of hydroclimatic change and thinking kind of broadly about nutrient loads. And, and I guess with an eye more towards some of the kind of larger scale issues, things like for example, the Bay is a good example where, that one, it turns out, just kind of loads are sort of a key driver to the response that you see in the downstream estuary. And but we didn't get into, other than how what the model, the individual watershed models were doing to represent changes in assimilative capacity, we didn't look into that in detail.
Okay. So from Andre, two questions, but the first one, my understanding of using A2 scenario is your extremes. How did you change the gridded GCMs to the watershed? And did you use inverse averaged method? And if you did, that would reduce variability and smooth out the extremes. So for the GCM scenarios, how did you go from the generic GCM result to the specific inputs to the models, I guess?
Yeah, and that was using this change factor approach where we had these deltas. We interpolated, from the GCM grid to the individual weather stations, the NCDC weather stations that were used in the models to set up to calibrate and validate the models. And then we just pulled, we just pulled up these historical this historical weather data observation over a 30-year period, roughly 1970 to 2000, and just we're adjusting those weather values to reflect the broader scale changes projected by the climate model. So that's how we developed the actual meteorological time series that were input to the models, and that was it was run at the daily scale. In HSPF, it was actually we ran it actually at an hourly time step and then aggregated up to the daily scale.
Okay. And then, how did you choose? I guess what parameters did you consider using the downscaling method? And I'm not clear if that question is general to sort of how do you downscale the GCM, or if it's specific to the particular regional models. So maybe you should address both. Okay. Sorry, it is a general question. So it's this general. Why did you choose? I guess why did you choose this delta method? And
yeah, over. Yeah. Well, we use that because, the alternative would be to just use the raw climate output from the climate models. And there are a number of issues related to that also. You get into issues with bias correction. I know particularly with the NARCAP data, there were some issues with bias correction that have been identified. We just kind of were able to sidestep a lot of those issues using this change factor approach. So we thought it was a simple but an effective way to do this. I actually like it because it is somewhat of a hybrid. It's the change factor approach itself is kind of a simple statistical downscaling approach where you can take a model, a broadly projected change from a climate model, and then be developing. In this case, you're developing a spatially explicit, spatially and temporally explicit, weather time series to be put into the model just based on adjusting historical observations across your modeling domain, but that reflect the broader scale patterns that you're seeing in the climate models, which is what we think are sort of better to begin with. It's, at the finer scale, there's some question of just how good these climate simulations are to begin with. So that was just a choice. The alternative would have been to go back and try to get the actual climate model output and be running, using those as the scenarios. But that was just a lot more work. And so this was to do the modeling at this scale. We just had to simplify.
Right. Tom, can you hear me?
Oh, I can. Yeah.
Yeah. This is Andre. So I think I couldn't ask my question very well. The thing is, I know how the delta method works or delta change works. My question actually is, because you use A2 scenario, my understanding is that you are more actually interested in extreme. So the first question I tried to ask was, so when you are changing the gridded GCM to the local watershed, the point you have, I don't know what method you use, but usually people are using the inverse like a weighted method to get the point in the watershed. So my feeling is, so this is actually smoothing out the extreme, and
I see. Okay.
This was my
Yeah. Okay. Sorry.
So,
I think Yeah. So yeah, the
right.
A2 is a fairly high. So it's would be reflecting relatively high greenhouse gas emissions. So it would be not only just the extreme events, but it would be affecting the mean climate as well as changes in the extremes. But yeah, so that work actually we partnered with NCAR, National Center for Atmospheric Research, and Seth McGinnis, who was with the NARCAP program, actually did that interpolation for us. We took the NARCAP data from the NARCAP grids, and each one of those models has a little different grid structure, which has made it a lot of work. And he did the interpolation to the NCDC sites, and it was, I think it was some kind of a spleen function. It was some kind of a relatively simple interpolation. If I could get back to you
okay.
exactly what that was, but I think it was a relatively straightforward. I think it was just a spleen function, interpolation.
Right.
The NARCAP is at a 50-kilometer grid, so the NARCAP data itself is actually a lot better resolution than for example, the GCMs, which might be more like a 200 or 300 kilometer resolution. But then it was from that, for the NARCAP data, at least from that 50-kilometer grid, it was interpolated to the the nearest weather stations. I think it's some kind of a spleen function, I think. But shoot me an email if it's something you're working on, and
Sure.
that's it would be helpful for you to know exactly what we did.
Right.
I'm happy to find out.
Sure, thank you. And my other question actually was, so I saw you're more interested in phosphorus, nitrogen, and sediment. Mm-hmm. And again, my understanding is temperature, for example, has a more effect in summer. So the extreme temperature So I was thinking to going backward. So we know that like certification happens in summer, and we choose the downscaling method based on our needs. And so I was wondering if did you any kind of a study or like assessment which downscaling method has a better understanding of the extreme events?
Yeah, I haven't done that. I consider these. They're all. Full disclosure, I'm not a climate scientist. I'm a hydrologist, but I guess I've absorbed some of this over about 10 years or so working on these kinds of studies. But I consider them. For example, if you compare the BCSD approach, which has been widely used and I think well respected as a set of scenarios in the NARCAP.
Right.
That they're both a good choice if you're doing a study. And there are certain assumptions inherent in each of these. The regional climate models. I think, as you see in our results, there tend to be more variability in among the different regional climate models. As you would expect, that if it's something at a real fine scale, or if you're in an area where, I don't know, convective storms, or there's some kind of a phenomenon that you think, would not be captured very well based on the observational data that that are available there, that, then maybe, selecting if you wanted to do using a dynamical downscaling approach might then be appropriate, as opposed to sort of capturing kind of larger scale patterns where the statistical approach might be more appropriate. But I think, I don't think you can look at the data sets and say, well, this one's better than that. I think they're both equally as good, but there might be some sort of physically based ways that you could reason, about in a particular place, a particular phenomenon that you're trying to capture in your scenarios that might be better captured by a certain type of downscaling. I would approach it that way from more of a theoretical point of view. But ultimately they're just scenarios too. I mean, these are not. I don't think of these as forecasts. These are just internally consistent, plausible alternative futures, and they give us a sense of what is likely, what is reasonable and likely for a particular place, and you can rule out certain things that we think are very unlikely based on what you're seeing in these scenarios. But ultimately, I think it's important to remember that these are just scenarios, and you really do need to be looking at multiple, an ensemble of sorts. You shouldn't be trying to pick one single approach or model to be basing any kind of, an analysis on. But those are, again, those are all great questions. I think there are people working on these, and I would hope going forward that, it would be wonderful to be able to nail down some of these questions, better as we go forward.
Thank you so much.
Okay, well, we are a little bit past the hour now, and so I'd like to first thank Tom Johnson for a wonderful presentation and a lot of information, and also thanks to Tom Meixner and Roy Haggerty and Patrick Belmont for suggesting and helping us arrange this seminar, and thanks to all the attendees. For people who do want more information, there is information. This presentation will be recorded, so within a couple days we'll have the recorded presentation up on the Quasi website for viewing and download, and there's also the links to the reports that Tom mentioned in his presentation in the abstract for the seminar that's up on our website now. And also just a quick plug, I hope you'll all join us at 2 weeks when we start our regular cyber seminar series. The spring series is going to be on snow hydrology, and the first one will be Friday, February 7th at 3 p.m. Eastern. So thanks everyone for joining us, and Tom, if you have any last words to say before we close up the call, I'll turn it back over to you guys.
Thank you very much for